Hello, my name is Nicholas Belston, and I'm a student of Aeronautics and Astronautics at MIT, and I conduct research with the Star Lab. Today, I'll be talking about the design and verification of a clock system for orbital radio interferometry as presented for the Small Satellite Conference 2020. First, I'll talk about the Aerovista spacecraft, the spacecraft which this clock system is designed for, and their target, the radio aurora. I'll talk about radio interferometry and its associated timing requirements. I'll talk about clock source design for Aerovista, and end with the next steps both for Aerovista and for orbital radio interferometry in general. I want to motivate this discussion with this pretty picture of the aurora taken from the International Space Station. You can see that it's interesting and complicated and beautiful in the optical bands, and it's equally so in radio frequency emission. The Aerovista spacecraft are a pair of identical 6U cube satellites, each with a 6-element vector sensor, which you can see deployed here. These antenna elements consist of 3 orthogonal loop antennae, which measure the magnetic field, and 3 orthogonal dipole and monopole antennae, which measure the electric field. Together, these antennae can derive information about the direction of propagation and polarization of a RF signal, even though all of these antennae are electrically small compared to the wavelengths that we're looking at. Each spacecraft also has an auxiliary sensor package with a magnetometer and camera, and a high-precision clock, which will be the primary focus of this presentation. Aero and Vista are designed to measure the radio aurora to answer questions in space science, to validate ground vector sensing interferometry in space using both the aurora and ground beacons. They will apply vector sensing interferometry to auroral radio emissions and characterize the low Earth orbit RFI environment. These are the targets for Aero and Vista, the radio emissions from the aurora. They consist of auroral kilometric radiation, auroral hiss, auroral roar, and medium frequency burst. Of these, auroral kilometric radiation is expected to be the most intense. It's important to note that all of these emission mechanisms are relatively low frequency, in the HF band or about less than 15 megahertz. This makes interferometry a little bit easier, and the spatial complexity of the aurora makes the aurora an interesting target for interferometry. You can see some of this complexity by recording the radio frequency signal and downsampling it to an audio band, as has been done by the University of Iowa and provided at the linked website. And since you're watching this asynchronously, you can follow that link and look at lots of other recordings of the aurora there. Next, I want to talk about radio interferometry and its associated timing requirements. Pictured here is a more typical interferometric array, the Very Large Array in New Mexico. Each of these parabolic antennae are operating cooperatively to synthesize a larger effective aperture. Radio interferometry requires separation in space and synchronization in time. This is achieved on the ground with hydrogen masers, which are very high accuracy clock sources. But cube satellites and other small satellites like Aero and Vista are too small to house hydrogen masers currently. In order to select the clock source, we'll first have to look at how these clock sources are characterized. This is typically done with the power spectrum, which represents the fractional power at a frequency offset from a nominal power, and the Allen deviation, which represents the fractional frequency deviation at a given time, after a given amount of time has passed. When you plot both of these on a log-log plot, as has been done here in cartoon form, you see that they frequently form these linear areas corresponding to different power laws. And these correspond to different noise mechanisms in the clock, namely white phase noise, flicker phase noise, white frequency noise, flicker frequency noise, and random walk frequency noise. It's not guaranteed that all of these noise sources will be in any given clock, but this provides a useful way to analyze and compare clock sources. We would like to derive a requirement from the science requirements for our clock system. For Aero and Vista, we have science requirements as follows. that the coherence loss be less than 15%, that we have a maximum operating frequency of 15 megahertz over an integration time of 100 seconds. We can conduct a 0th order approximation of how accurate our clock source will need to be by requiring that the RMS phase error be less than 1 radian over our integration time. And this can be evaluated relatively simply to find an approximate requirement of 1 times 10 to the negative 10 for the Allen deviation at 100 seconds. To get a little more formal, we can look at the coherence loss, which is defined with the equation for LC on this slide. This is defined as a function of the coherence of the signal over the integration time. There are analytic expressions for the coherence loss due to white frequency noise and white phase noise, and we can perform some approximations and use numerical methods to evaluate the coherence loss due to other noise sources, as has been done in the paper associated with this talk. You see here that we have applied a linear fit or a power law fit to both white frequency noise and white phase noise with the K0 and K2 terms. So we can look at the Allen deviation of a clock, pull off the intercept of the different power laws, and then derive a resulting requirement analytically. This has been plotted over 100 seconds in orange and blue for the different noise types. And we can see that we have a requirement, a 15% coherence loss requirement of about 1 times 10 to the negative 10 seconds, like we saw on the previous slide. Now, when we perform interferometry, we can search for a kind of stretch or shift of the signal, which maximizes correlation, which allows for a slight relaxation of the timing requirements. And using these techniques, we've set a requirement of 5 times 10 to the negative 10 for the Allen deviation at 100 seconds. Next, I want to move on to the clock source that is expected to meet all of these requirements. Pictured here is our design of the clock board in our PCB design software. First, we want to select the high stability reference source. We will compare these reference sources with the Allen deviation. Pictured here is the Allen deviation over integration time for a number of different high quality clock sources, and our requirement is called out in this purple diamond. It would seem from this plot that all of these clock sources would easily meet our requirements, and they would easily meet our timing requirements, but these are all high quality clock sources that are intended for ground applications. The quartz oscillators, for example, are likely representative of large ovenized quartz oscillators that consume lots of power and would not fit in our satellite. Therefore, we've selected a chip scale atomic clock, which both has high stability, as pictured on this plot. It meets our timing requirements, it meets our temperature coefficient requirements, and is relatively low weight and low power. In addition to long-term stability, our clock system has to have good short-term stability. This is frequently represented as phase noise, or its integrated form as jitter. This is because the clock system drives RF ADCs that sample the signals coming off of all of those antennae. These ADCs need a stable clock source, and as pictured here, we see that the SNR of an ADC degrades with increasing frequency and with increasing jitter. This is a picture from the datasheet for the analog to digital converter that we are using, and we see that we experience significant SNR degradation even with only a few picoseconds of jitter at 15 megahertz. Therefore, we're going to require that the clock system have less than 1 picosecond of integrated jitter. To meet these requirements, we've selected these major components: the chip-scale atomic clock manufactured by Microsemi, and the 809545 PLL, which is shown as the little integrated circuit on its evaluation board here. The clock system is a fully integrated system that includes the electronics to communicate with the rest of the spacecraft. It provides its own power supply filters, as well as health and status analog to digital converters. The communication with the rest of the spacecraft occurs over SPI, and this was selected for this was selected over I2C for its lower EMI emissions, which is important for our vector sensor payload. In the timing chain, we have the chip-scale atomic clock, which can be disciplined by a GPS pulse per second signal, and this serves as the reference for the PLL clock synthesizer. This clock synthesizer is somewhat unique in that it can also be disciplined directly with a pulse per second signal, so even if our chip-scale atomic clock fails, we can still derive a reference clock using the clock synthesizer by disciplining it with the GPS pulse per second. As designed, the clock board is expected to have these system specifications. The board area is 50 centimeters squared, the total power consumed is less than 1.5 watts. We expect an Allen deviation over 100 seconds of about 3 times 10 to the negative 11, a clock jitter of 0.3 picoseconds, and a clock temperature coefficient of about 6 times 10 to the negative 12 per degree Celsius. We've started verifying some of these parameters with the test setup pictured in this block diagram. We have a GPS receiver serving as the discipline source for the CSAC, which itself is disciplining the 809545 clock synthesizer. This is routed into one input for the Symmetricom 5115A phase noise and Allen deviation measurement rig, and that device is disciplined with an ovenized benchtop crystal. Using this test setup, we've measured the Allen deviation pictured on the right, and this is plotted along with the expected values from the datasheet. We see that we're easily meeting our expected Allen deviation at 1 second. It was supposed to be less than 3 times 10 to the negative 10, and we see that it's down in the neighborhood of 1 times 10 to the negative 11. We also expected a transition from white frequency noise at greater than 100 seconds, which we do not see on this plot. Instead, it's happening at about 1 second. This is likely because we are not directly measuring the characteristics of our clock system, but just comparing two clock systems, our clock system with the ovenized benchtop crystal. As we saw a little bit earlier, these benchtop crystals are high accuracy clock sources at low integration times, but not so much at higher. Therefore, to fully measure the Allen deviation of our clock system, we will need to test with a higher quality clock source like a hydrogen maser. Using the same measurement setup, we've measured the spectral noise density, and we verified that we meet our requirement of less than negative 110 dBc per hertz. We can't directly calculate the integrated jitter from this plot because the bandwidth of the measurement setup is not high enough, but the measurements that we have conducted match the datasheet parameters, so we expect to be able to meet our requirement. Pictured here is the actual manufactured engineering model for the clock board that we've just received. The chip-scale atomic clock has not been populated yet, but with the hardware in, we expect to conduct some of these more high-quality tests in the near future. I'll end with talking about the next steps for Aerovista and for radio interferometry. In the near future, we plan to measure the clock performance for Aerovista to higher fidelity and verify full system performance after integration with the rest of the spacecraft. Next, we'll launch Aerovista and verify interferometry performance with HF ground beacons. Looking farther into the future, precision small satellite timing is useful for lots of payloads, such as communications payloads or precision ranging payloads. And interferometric array performance scales rapidly with the number of receivers. So these small satellites with high precision timing payloads have the potential to be very powerful measurement sources. And finally, higher performance chip scale atomic clocks are being developed, which will unlock even greater measurement potential. In summary, interferometry enables high angular resolution remote sensing applications, and interferometry requires stable clock references. The clock source as designed for Aerovista is expected to meet the requirements for interferometry, and new developments in chip-scale atomic clocks will enable more capable interferometric arrays of small satellites in the future. These are the sources for my images and content, and I invite any questions at my email. Thank you.